Okay, so now here's a different concept altogether. This is a special case of a structure. Here we have like an L-shaped bracket, and there's no load applied to along the length of it, okay? But like maybe this is a bolt that this force is representing, and there's a bolt over here, and it's like a linkage inside of a mechanical system, right? So it's getting, forces applied to it at each end, and it's linking two things together. Can this structure exist with the forces on here as shown? Can the forces applied at each end look like this? Did you answer yes, or did you answer no? If you answered yes, I would ask you to sum forces in the x and the y, whatever your x and y are. We could say x is pointing to the right, and then y is pointing up. These don't equal 0. They don't. It might even be another good way to do it is call your x-axis the line that connects these two dots and sum forces in that direction, right? That, obviously, this does not work. This even has moment all over the place, right? This is a terrible setup. If you sum moments about A, FB is causing a clockwise moment. What really has to happen is that FB here, this force has to go through point A, and FA has to go through point B. That way, there's no net moments ever generated. And so what the actual orientation always is this. Now, when I say always this, it can point towards, both of them point towards each other, or both of them point away from each other along that common line of action. And that is really, really cool and convenient because now we understand the orientation of the force in this member without actually calculating it. We at least know the orientation of it, and that can be huge. So this is called a two-force member. Why is it called a two-force member? I hope you can guess why. One force, two force, right? Two-force member. It has forces applied at each end, no force is acting along its own length. And so that even means like you have to neglect its weight and everything, which we often do in statics. But you can't have applied moments. You can't have like rigid ends. It has to be pin connected, and it's got to be no forces along its length. And then you've got, boom, you got a two-force member. So cables, like the rope stuff that we did earlier on in this semester, those are all two-force members. Ropes and cables are two-force members. Linkages are two-force members. There's a ton of two-force members out in the world. Ropes can only be in tension. Their arrows can't flip where they're pointing towards each other because they can't handle compression. But if you had like a pipe between two people, like playing tug of war with a pipe, you could both pull away or push towards. But they always either point away from each other or point towards each other. They never both point, to the right or, to the left. Examples of a two-force member. Well, this hydraulic jack and that hoist that we were talking about earlier in the slides, that's a perfect example of a two-force member. Think about it, when they make these things, they're not really meant to be pushed side to side. If you push this thing side to side too hard, what you're going to do is bend this piston, and it's not even going to work anymore. This thing is absolutely meant to work as an axial force member, either compression or tension, and oftentimes these things are tension. But think about like a backhoe, like somebody's using one of those buckets to scoop a ditch out. These things are what open and close the bucket and open and close the arm, and they can work in tension or compression. They're two-force members, though. If you look, it's connected with one bolt at the bottom and one bolt at the top, and that's done very much on purpose to make sure that there's no moment generated up top. They're trying to make this a frictionless pin, right? That one, a frictionless pin, so that none of the moments can transfer across, and you've got a two-force member.